If I were to ask you guys this question, no, let me just ask you guys this question, not put in the form of an if question because that makes it a rhetorical question. This is a real question for you guys. So I need everybody to pay attention and try to answer this question for me. So raise your hand. All right. What is it that makes something a science? What do you do that makes it the way science is done?
Could you word that better? Control a variable?
Okay, control variables. What? Record data. Yep. Experiment. Okay.
It's just find knowledge.
Apply what?
Apply knowledge.
Apply knowledge. Huh?
Questions.
Labs. Question.
Live. Observe.
What'd you say?
Observe.
Observe. Okay. Huh?
Live.
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 Okay. You think everything has to do with living is science?
No, but when you live, your body is alive, so your body has to be moving, and that's science.
Okay, well, you can apply it in that way, I suppose. That's true. But I'm looking for things that are actually part of how we do science. Okay? Living, yes, that's part of how we do science, but living is a lot more than that. I want to narrow it down to those things that are just part of doing science. Observing is part of doing science. Okay? Testing is part of doing science. Labs will be part of testing. Okay? So what else makes something a part of how we do science? I mean, you've been taking science classes since, I don't know, they might not have been called science classes, but you were taking science subjects since first grade. Okay? Huh?
Write a hypothesis.
Writing hypotheses and testing hypotheses are part of doing science. Okay? Is there a single phrase, word, title that sort of describes this whole process? Have you ever heard the phrase the scientific method?
Yeah.
So you've been learning that for a long time, right? Okay. There's a problem with that. And I know you've been learning about the scientific method for a long time, but we're going to unlearn some of that, I hope. Now, here is a problem that is scientific, because we know the research is there that shows this to be true, or as true as science gets to being true. And I say that I know that sounds kind of funny, but science doesn't prove things, okay? Science is about disproving things or offering support for things, but it's not about proving things. So when somebody says they're proving something, they're not really doing science. Every time you see a commercial where somebody says, "Proving my science," that's a lie, because science doesn't prove things. Now, having said that, even scientists themselves sometimes say proven. But when we say it in the sciences, we understand that everything in the science is subject to revision. So when Newton proposed his laws for the motion and such, that stood as being the gold standard for hundreds of years. But about the time that Einstein came along, a lot of scientists, a lot of physicists knew there was something wrong with some of those laws, particularly around very big things and very small things. And so Einstein was able to solve the problem by proposing a solution to it, and in a sense disproving some of Newton's laws. All right. We don't prove things in the science, or we prove things that's sort of tenuous. It can be pretty solid for hundreds of years, but if somebody comes along with the evidence to support something different, then scientists, if you're really scientists, have to be willing to accept the fact that, okay, this is not really working anymore, or it only works under certain conditions, which is the way Newton's laws work now. We still use Newton's laws all the time. I teach AP Physics. We use Newton's laws all the time, because we never get into the really big stuff or really small stuff where we have to throw that out. So you can, with Newton's laws, for example, you can use them 99% of the time, but you have to know there's that 1% where it doesn't work and you use something else. Okay? So science is tenuous. You never really prove things. You offer support or proof of things without really ever getting to the point where it's absolutely all the time, never again changed, proven. If somebody claims it's never again proven, you never have to change it, that's not science. Okay, now, the scientific method is a wonderful step-by-step process that you need to know, okay? Because those steps are valuable and helpful and useful. The thing is, Einstein, for example, didn't use them. Okay, now I see some of you look at your computer screen, and what we're talking about right now is not on your computer screen. So let's close down the cover of your computer for a moment. Okay, I need your attention up here because what we're talking about right now is really important. Okay, when the test comes around, you're going to wish you paid attention. Besides the fact, we're talking about taking a science class. So why are you taking a science class? You need to know what science is. Science is about discovering things in a certain way, and we want to know we want to know why we do that. It's not just because the school district or the state says you got to take science. It's because it's valuable to you, and if you're not listening, you don't know how. Okay. The scientific method is great, but Einstein didn't use it. What are the steps in the scientific method? Yeah.
Like problem, hypothesis, materials, procedure.
Okay. So you got, and different textbooks have it written out a little bit differently. Okay. They highlight certain steps, and some have certain steps that other ones don't. So you got some kind of a problem, or maybe it's not really a problem, but you have a question you want to answer. All right, that can be answered through some kind of testing or experimentation. And then you propose an hypothesis. Well, there's a step in there that often doesn't get mentioned that's really important. Okay, but with the hypothesis, and by the way, if you want a definition of an hypothesis, and you need to know a definition of an hypothesis, you need to know a definition of an hypothesis. It's not just an educated guess, okay? In the sciences, it's not an hypothesis if it isn't a proposal for what you expect to happen, okay? So it's, in a sense, it's an educated guess, but it's only an educated guess if you're applying it to things that you think will happen. It's not useful and helpful unless it's written in a form that can be tested. Now, I don't see anybody writing this down, so I assume your memory is really, really good, or you be writing it down, because I said you need it, right? Huh? You could write on the back of that, but we'll get to that in a minute. Okay, you'll see that in a minute. So an hypothesis is more than just an educated guess. It's a proposal for what you expect to happen. No, I'm going to get to a lot of writing, but I'm not going to do that right now. Okay, so a hypothesis is something, what do you expect to happen? It's not just an educated guess. It's a statement of what you expect to happen. But you can't just state what you expect to happen. Huh? You have to say why you expect it to happen. Exactly. You have to go, the word is cause, C-A-U-S-E. There has to be a reason to cause what you expect to happen. Okay? You have to have a reason, be able to state the reason why you think it's going to happen. Okay, that's the cause. For it to be useful, for an hypothesis or a hypothesis to be useful, it has to be written in an if/then form. By that I mean you write something like, if I do A, then B will happen. Does that make sense? That's much like those titles for those graphs. we talked about yesterday. If, with the graph title, I said you want to write the effect of the independent variable on the dependent variable. That's the graph title you use in this class. That is the hypothesis, in a sense, worded a slightly different way. If I, in the case of our last lab, if I increase the salt concentration in a solution, then I expect what to happen? The solution will become more dense. That's an hypothesis statement, if, then. That makes sense? So hypothesis statements, to be useful and helpful, and you be able to use them in a scientific context, they need to be stated in an if-then form. Okay? All right, so back to the scientific method now. Okay, so let's see. We started out with a problem, or it could be just a question. And then we said we're going to write an hypothesis, but I also have added in here, it's got to be a useful hypothesis that can be tested. If-then forms allow you to test things. So you can sometimes write if-then, so it's not testable. So an hypothesis has to be testable. You got to be able to test it to see if it's true. Okay. Let's see. Next step in the method would be some kind of testing, gathering data, doing experimental testing in a lab. But you've got to test the hypothesis in some fashion. Okay. And then, although different authors write it in different ways and have different steps sometimes, one common thing is you reach some kind of conclusion at the end. Okay? So, problem, question, hypothesis, testing, conclusion. If I were to summarize all the different ways that authors have written the scientific method, those are the steps that I would say is pretty much common to all of them. Now, usually a conclusion is about saying whether the hypothesis is right or wrong, or, let me back it up, is supported or wrong, okay? Because remember, we don't prove things, and saying it's right would be saying it's proven. It's not proven. So a conclusion is about saying, usually, that your hypothesis is supported or is disproven or wrong. The last lab we did, you wrote an hypothesis, but your conclusion went beyond whether your hypothesis was supported. The hypothesis was about whether the graph would behave the way you thought it was going to behave, whether concentration was going to give you a change in density or not. Ultimately, you're going to use that graph and that support for your hypothesis to show what the concentration of the unknown is. That was the ultimate goal. So in a sense, proving or disproving the hypothesis in that lab was an interim step toward the end step, which was to determine what the concentration of the unknown was by using that graph for that purpose. Okay? All right, so those steps are great steps. You need to know those steps. You need to know that's the way science is often done. But if we were to apply Einstein, the name that everybody mentions when you say, well, name a famous scientist, Einstein's always comes up.
He's the best scientist.
Well, I wouldn't say he's the best known scientist, okay? I wouldn't say he's the best scientist.
He made the most.
He what?
He made the most.
Like money? No.
Science.
He made money, but he didn't make the most money by any means, okay? There are scientists who've invented some processes that made them a lot more money than he did.
Somebody told me that he would be richer than Bill Gates if he was alive.
Really? You believe everything you're told?
That's not a bad thing to believe in.
No, belief is not a bad thing, but scientists also want to be just a little skeptical about just about anything. Okay? Einstein was not uncomfortable. He had a comfortable life. Okay? He was a college professor, and he made money in other ways as well. But he wasn't, super rich in the same category as Bill Gates by any means. Okay? and wasn't even probably headed that direction. But anyway, that's beside the point. The point is that Einstein did not follow the scientific method. Einstein didn't do independent testing, didn't do the hypothesis and conclusion steps. What he did was he took the experimentation that had been done by other people and the questions raised by those results and proposed a solution. So he kind of skipped over all the testing part of it. Okay, he didn't follow the scientific method. But we would call him, almost everybody does, a great scientist, right? He knew the scientific method, certainly would have followed it if it needed to be followed, but for what he did, it didn't make sense because the testing was already done. He just proposed the conclusion at the end. Okay? So the problem with the scientific method, that phrase, the scientific method, is the word the. The problem with the scientific method is the word the. Okay? The problem with the scientific method is the word the. It's a great step-by-step process to remember, but sometimes you don't always follow every single step like that's the only one. It's not the like it's singular. Okay?
How was Elon Musk a scientist? You know, Elon Musk is the.
Yeah.
He used to be
He's like a
Tesla.
scientific engineer.
Yeah.
He's a billionaire.
How would
Yeah.
making Teslas or designing Teslas be science?
Well, I don't want to get too far down this road. He has degrees in science, all right, but he's more of an engineer and an entrepreneur than a practicing scientist. Okay? That's not to say he doesn't do science, but he's kind of like moved beyond that for what he does.
He just
He's
fell
a
into that
physicist.
category.
Huh?
He just fell into that category.
Well, he is a scientist in the sense that he's trained for that, and he sort of began in that realm, but he's kind of moved into entrepreneurship and engineering now. Okay?
He's a physicist and he loves astronomy.
Yeah,
But he's mainly just a gifted scientific engineer.
yeah. I would say yeah, you're looking that up on the internet. I told you to close up a computer. I'm just saying, you know. Okay. All right. All right. Let's talk about how science really gets done. Okay? Because the scientific method doesn't mention anything about the real goal of science, what science is really all about. So we're going to look at what science is really all about today, how science gets done. Okay? Because not all science necessarily follows a scientific method. It often does. And it's a step-by-step process that every practicing scientist needs to know. Even people that aren't practicing scientists need to know it. But you also need to know that you don't have to follow the scientific method to be doing science. Okay? So that Einstein is a great scientist even though he didn't do science. All right. So you have a template to work with. All right? And in the very middle, we're going to talk about what science is really about. Okay? And this may surprise you. I hope it does. Because my guess is, here's the problem, or here's a problem. What you believe when you come to this class often is what you believe when you leave this class, even in the face of evidence that would tell you otherwise. If you may find there's a ton of evidence that would disprove what you believe, but you're going to believe it anyway. Most people only accept evidence that supports what they believe. And scientists need to be willing to accept evidence that is contrary to what they believe. And if necessary, revisit. Doesn't mean you have to cease your belief, but you need to be willing to at least look at it. You know, that's only fair. That's only reasonable. Reasonable people need to be able to look at those kind of things. Okay, and if you don't believe the evidence, you need to have a reason, a substantial reason for saying that. Be able to state that. Okay, not just because you don't believe it. You know why? That doesn't make any sense. You believe it because you don't believe it. That doesn't make any sense. You need to be able to, and for scientists, in a science class, You need to be able to state a reason why you accept something or don't accept something. And it has to be substantial. Okay? All right, so the goal of science, the real goal of science, the ultimate goal of science is not just to find out stuff. Okay? It's not just to find out whether concentration of salt increases the density of a solution. The real goal of science is to argue, is to develop defendable, remember we talked about being able to support it? Okay? Defendable arguments. That's the support part. Defendable arguments to explain the way everything works, the universe, how it all works. Those arguments, when we say defendable, we mean they're based on natural explanations, which is to say physical explanations. Can't just be any explanation. It's got to be defendable, based on the things you can observe, the things you can measure, the things that can be tested. So evidence, physical explanations, sound reasoning. So that just doesn't mean just any kind of reasoning. It's got to be sound reasoning. Sound is a kind of a fuzzy in this context. Sound reasoning doesn't mean fuzzy, spurious. You've heard somebody argue something that doesn't make any sense before,
They call him a furry.
huh?
They call him a furry.
A what?
Furry.
3.
No. You ain't never.
Furry?
I don't think you've heard that.
Apparently not.
Just look it up in your private time.
Well, he and I have been going round and round about unusual words, so
Oh yeah.
yeah.
You've never heard anybody say.
It doesn't matter. Let's don't go there. Let's don't go there. All right, now,
Just look it up.
so sound reasoning doesn't mean just any kind of reasoning. It means when reasonable people with good judgment can understand something. Okay? And unfortunately, there's a lot of people who don't have, they aren't very reasonable. All right? Now, one of the things that gets left out of the discussion about that scientific method is we don't talk about all the knowledge of science that's already been accumulated. And that's where the science begins when we're starting with it, when we start with it at this point in time. So a lot of science has been done, a lot of published work in textbooks and on the internet, various places. We already know that there is something called an atom. We already know that there are structures of atoms linked together called molecules. That knowledge is already done. We already know how they behave to a large degree. Why would we reinvent that? We can take and start with that as a beginning point for us to move forward. And so one of the things that's really important in science is that information that's already been obtained and organizing it so it can be found. There are these internet databases and books, source books that have been published that have tons and tons of information about things that are already known. We want to start with that as our beginning spot to move forward. Otherwise, we're reinventing the wheel. Why reinvent the wheel? Okay, we want to move forward instead. But in addition to what we already know, we need to have sort of figured out what we need to know. When Einstein came along, there were scientists who had accumulated knowledge that showed that a lot of what Newton said didn't work in certain cases. So he had questions already out there for him. Somebody had already organized and said, this doesn't seem to be in line with what Newton said. And so that was a starting place for him to begin his work. And that's where science often gets started for somebody who's doing research. All right. So once we have that beginning place and we have what we know and what we want to know, then we can start writing hypotheses. Then we have a basis to write an if-then statement, a predictive statement that can be tested. Okay? But if you notice, I didn't say we just write hypotheses. I wrote a statement in which we say it's based on a model. So that word model often gets overlooked. Often isn't even included in discussions of science. And the reason we can write an hypothesis to say, if I do A, then B will happen, is because I have a reason to expect it to happen. I know I have a suspicion about what would cause it to happen that way. The why you were mentioning earlier. Okay? The cause is the why or the how. All right? So the model is about, it's not just enough to say, if I do A, then B will happen. I've got to explain why I believe that will happen by explaining what would cause it to happen. Okay? Otherwise, it's just a spurious statement. It's fuzzy. It doesn't make any sense. It's not reasonable. Okay? You know, I can say, I think you're going to fail this class because you're lazy. But I have to have a reason for saying that. Or I could say, I think you're going to make an A in this class because you're really smart. But I got to have a reason for saying that. All right? That makes sense? And by the way, everyone in here is capable of passing this class with a good, solid grade. Everybody.
Effort.
You got to do your work. It is mostly effort. It is mostly effort. Okay?
This is my last question.
You promise?
Yes.
Okay. No, you can ask more questions. So, we build these hypotheses based on what we already know, and we build them based on a model. And a model is an attempt to explain the cause. A model doesn't have to be right. If a model is already right, if the hypothesis is already known to be true, why bother testing? Okay? You have an hypothesis because you don't know for sure. You're proposing this as a possible reason. You're proposing the hypothesis as the logical result of that cause. But we're testing it to see if it's right or not, to see if it's supported. Okay? If it's not supported, then it's not true, and we disprove it. We never prove things. We support things. We have evidence to suggest that it's true. We can disprove things, and science is, some people would say, and I would say in certain contexts, science is not about proving things, it's about disproving things. But we're also about supporting things too. Okay? All right, so we organize what we know, what we like to know. We generate hypotheses, and both of these go toward that goal of science. Okay? Both of these go toward that goal of science. I heard somebody say they didn't get what it said about models. An attempt to explain the cause for things that might happen or that do happen. Okay? All right. Now then, once we've got an hypothesis based on a model, then we can go about testing that hypothesis. Okay? And science is about testing everything. We can't test a model. Hypotheses are written as a logical extension of a model. We can test hypotheses. If the hypothesis is disproven, often that also means that you're disproving the model. Not necessarily. It might have been the test was flawed. Okay? So you can't test a model. You can test an hypothesis. So the hypothesis is the physical part that you can test based on what you think is the cause for it happening. Okay, so we're really kind of dividing this idea of the way science works into two categories. The things that actually do happen and the cause for those things that actually do happen. Okay? You can't test the cause. Well, I'm sorry. You cannot always disprove the cause. You can disprove an hypothesis, okay? If the hypotheses are sound and you've got different hypotheses approaching the problem from different points of view, you might eventually disprove a model, okay? But directly disproving a model, it's like that doesn't make sense. Okay, it's the idea of what you think is causing something to happen. All right. So we go from hypothesis to testing of the hypothesis, and we're going to seek evidence. Sometimes that means testing in a lab. Sometimes it means going out in the field and just gathering data that's already done, okay? And then we go about this process of constructing an argument. And it would seem like, okay, we finally reached the end, that must be easy. It's not. Constructing an argument involves peer review. Now, in the English and literature classes, when you peer review, what you mean by that is that somebody else is reading your paper and telling you whether your grammar's right and your structure's right, right? Yes? Okay? But that's not the kind of peer review in the sciences we're talking about. In the sciences, peer review means they're looking at your concept, of your research. Was the research sound? Were you actually testing with the hypothesis the model you proposed? Are you doing good science or are you doing bad science? So it's much more than just looking at whether your grammar's right. It's whether your ideas are sound or not. And that's really hard. That doesn't mean that the people who are questioning it are angry or upset, and they're not always very necessarily nice, but, it's really hard on somebody who's spent 20 years working on something. They've got a logical conclusion to a problem or a logical conclusion to a question, and lots of these other scientists saying, well, this is a problem with it, that's a problem with it. It's like you're attacking their whole life because their whole life was built around that. So it's kind of tough. It's a tough thing.
Some people live their whole life around one nice question,
Sometimes, yeah.
and they get paid off of it too.
Huh?
They get paid off of it too.
Sometimes, yeah.
Like scientists will get paid to figure
Sure.
out something for like 20 years or
Sure.
kind of.
20, 30, 40 years, 50 years. Yeah,
So it's our tax dollars just going down the drain.
could be. It's happened. Yep. All right. So they go to a conference and stand up and tell everybody about their work, and people find all kinds of problems with it. Now, usually you don't shoot down everything, but you say, well, this is a problem, that's a problem, you have to go back and revise. But sometimes the whole thing gets shot down. It happens. It's kind of rare because usually it's around the edges, the little things that build up to the big thing, and sometimes you got to go back and revisit everything and redo testing or research or whatever. So it happens. All right, but scientists know it's coming, so they try to head that off and making sure they've covered everything. All right, hopefully avoiding any bias.
So do they have other scientists look at their proof before they?
Sure they do. Yeah, I would if I were going to go present something at a conference or submit something to a prestigious journal somewhere. I'd want other scientists to read it before I even get there. Sure, absolutely. All right, and so there's an old adage or proverb in the sciences: every time you find an answer, there are 10 more questions. That kind of goes to this. Every time we find a reasonable argument that makes sense that other scientists accept, there's just new questions to be answered. So science never stops. So you were asking a while ago about whether science is continuing to move forward. Absolutely, because it's circuitous. It goes around in a circle. It keeps building and building and building and building, and you keep adding the knowledge in a mathematical way called exponential. And what that means is the amount of new knowledge doesn't just increase like double from one year to the next. It increases like 10 times in the next year and 100 times the next year. That's an exponential change. Okay? So that's the way science really gets done. Science is about finding out what causes the universe to work, but we don't know absolutely, completely, final end of the discussion why it works the way it works. We're proposing arguments that it seem to explain in the best possible way why it works, how it works, the way it works. And then if a better argument's found, we have to go with that. That makes sense? Okay. So that's how science really gets done.